Okay, so in this section, we are going to learn a new strategy for integration. In the last section, for trig integrals, we were trying to be creative and crafty and use trig identities in a way that we could just use our old basic U substitution method. In this particular section, we are going to learn a new method called trigonometric substitution. So instead of a U substitution, we're going to make a substitution with a trig function. So I have a couple of startups here, as usual, to try to get you ready for why do we need something else. We already have U substitution, we have integration by parts. Why would we need something extra? So just to walk through things that we already know, you already know how to do all 4 integrals on this paper. So if you want, you can pause the video, work on them out, and then just sort of move ahead. It's a good practice. This section, this unit 3, is all about integration and being able to do old integrals and new integrals. So if I just kind of walk through question 1, this is your basic U substitution. It's classic in the sense that you are just going to let U equal whatever's inside that function, that square root function. It's a composite function. This is exactly how U substitution was designed to work. And anytime I have a U substitution, of course, you're going to have a follow-through. And I'm going to solve that follow-through for the dx. So I have a good substitution going on there. So I'm going to go ahead and make that swap. My integral was the square root of something. I chose to let all that stuff underneath be u, and in place of dx, I'm replacing it with du over 9. Okay, so I'm just going to go in here and take that 1/9 out. I'm really integrating u to the 1/2 du. And so I'll get that antiderivative. Add 1 to the exponent, divide by my new exponent, and put all these puzzle pieces together. I can't box up this answer because it's in terms of u, and my integral was in terms of x. So of course I will switch back. And there is my final antiderivative. Again, basic U substitution to let that work. Moving on to number 2, slightly different variation there. I do have a radical. It's in the denominator. And if you look at this, this is, well, should be, hopefully, a recognizable integrand. This looks like some version of the derivative of arc sine. So I'm going to use that approach. Okay, so these are all things that, we've certainly discussed in this class, but it all sort of comes on the same sheet of paper here. I am going to realize there's a radical. I have a number squared minus a variable squared. So I am going to say, I'm going to let a be 3, and I'm going to let u be x. And so anytime you're doing any kind of substitution here with u, of course there's a follow-through. Du equals dx. That's going to come in handy in a minute. And I'm going to switch this integral over. Let's go over here. And my integral now becomes, I'm going to try to squeak this in here, 1 over the square root of a squared minus u squared. And in place of dx, I can just slap the du on there. So this is the derivative of arc sine, and so I'm going to run to my answer here. My answer to this would just be arc sine of u over a. So for me here, that means my antiderivative is arc sine x over 3 plus that constant of integration. Okay, there we go. All right, so these are things that we've talked about in the past. All right, let's move on and go with our next 2 here. Again, these are things that you can do. Number 3 is a little annoying because I guess it is a U substitution, but I'm going to have to get crafty with it. We talked about this before. I am going to use that same strategy of say, you know what, let's let U equal that thing underneath the square root, that thing inside a composite function. Very similar to number 1. I have the follow-through, of course, and du over 9 is dx. And so I'm going to transform this integral. We end up with a glaring problem, as you can see. There's this x that I haven't touched out here. And I can say, okay, this is going to be the square root of u, which is great, and I can do that follow through and put in the du over 9. But we have this kind of issue here with that x there. That's not allowed. You can't leave the x in there, but you can be crafty and rearrange our substitution to make it work, meaning I have this really good statement for u in terms of x. Remember, you are allowed to wiggle this around. This is not, quick, but I can take this statement, just swing the 1 over to the left. That would be u minus 1 equals 9x. And then if I just multiply both sides of this equation by 1/9, then I get an equivalent expression for x. So you're certainly permitted to do this. I am going to replace this x right here with what it legally represents. If you're the one that said that u was 9x plus 1, well then you can maneuver this around and have a equivalent replacement for x. So I'm going to use that. In place of that x there, I'm going to write this 1/9 u minus 1. I still have the square root of u there, and then I have this extra du over 9. So I'm just going to pay attention to those coefficients. I'm going to dump both of those outside the integral. That would be 1 over 81 as a coefficient on the outside. Now what I also am going to do is handle, well, how do I integrate u minus 1 times u times the square root of u? I guess I'll just write it. Here's where you use your algebra skills and say, I'll just multiply that u to the 1/2 in. All you have to do is add exponents. I've done a whole lot of work, and I've done zero calculus in terms of integration, so now I'm going to actually integrate it. So this is going to be u to the 5/2. There's a 2/5 coefficient in front. This is going to be u to the 3/2 with a 2/3 coefficient in front, and then of course we have to switch back to x. So these coefficients are really wild and pretty big and annoying looking, but I'm going to make sure that I move that 1 over 81 through. So that would be 2 over 405 for that coefficient. Now I have u to the 5/2, so I'm going to write 9x plus 1 to the 5/2. I'm going to distribute that 1 over 81 to the 2/3, and that would be 2 over 243. Again, switching back to x, that would be 9x plus 1 to the 3/2. And there is my constant of integration. So it's doable. It's very crafty and algebraic. It's still a u substitution. You can make it work here sometimes. And here it worked out for us. Okay. So the last one on this page, just to refresh your memory of things you already know how to do without this new method of integration, would be number 4. And once again, this is a basic u substitution. U substitution is the most used method by far. Because even though we're in our kind of fancy integration zone, we still rely heavily on u substitution. So I'm going to, again, let the u be the thing underneath inside that square root. And so I'm going to solve this for dx equals. And I'm going to transform that integral, again, just a basic u substitution. I decided to let u equal that whole thing underneath that radical, and in place of dx, I'm replacing that with du over negative 2x. So this is great because the x's cancel. I needed them to go away. I don't have to do anything fancy like I did in question number 3. The x falls off, so that's good for me because now what do I have? I have a negative 2. That's going to be a negative 1/2. Outside. Now that's 1 over the square root of u. That's u to the negative 1/2 power. And then I'm going to integrate from there. So I'm going to add 1 to the exponent, divide by my new exponent. Remember that there was a negative 1/2 in front. And then of course switch back to the x variable. So these are all things that you already know how to do, and you need to know how to do. These are all fair game for the Unit 3 test. So Unit 3 is, I'm going to throw a bunch of integrals at you, and you're going to have to diagnose the problem, whether it's a basic integral or u substitution or inverse trig, integration by parts, and kind of deal with all of them. Now, what we're going to work on in this particular section of our new method, what other things do I need to work on that I don't have the skills yet to do? And that would be 5 and 6. These two integrals are not great because I can't do a basic u substitution here. This is going to fail. Because when you do that follow through, you're going to have a negative 18x, and you're not going to be able to get rid of that. That's going to be a problem for us. It's also something that is not going to work by integration by parts either. It's not. This is not a great. This right here is not something that we know the integral of, so it can't be dv. It's also really complicated to take the derivative. So integration by parts is not going to be the way to go either. If you look at number 6, I have the same crisis. You know, here I have that square root of 9 minus x squared. Once again, u substitution is going to fail here. And integration by parts is not going to work out for us in this particular case. So what I want you to think about with u substitution, or I'm sorry, trig substitution, is when I have something that u substitution fails or it looks really complicated, and I also happen to see something going on in the integrand, I'm going to trigger to use a trig substitution. That's going to kind of be my idea. And what's going to trigger the idea to use trig substitution is when I see a lot of like number plus or minus a variable squared, where u substitution doesn't do the trick. But I happen to see a lot of this. Here I have 1 minus 9x squared. Here I have 9 minus x squared. I can kind of work with this and create a u substitution. And here's how it looks. Okay, it's trig substitution is really good at getting rid of a radical in the integrand that has a particular look to it, where again it's a number squared minus a variable squared. Depending on the order, we'll make different trig substitutions. Depending on whether it's subtraction or addition, we'll make different trig substitutions. But the whole point is we want to eventually be able to eliminate this radical. I want this to go away. And what we're going to have left is we're going to have an integral with trig functions in it instead of x's. Okay, so just like u substitution, when you make that switch, you have an integral with u's everywhere instead of x's. When I use trig substitution, I'm going to get rid of the x variable and replace it with a bunch of trig functions. So this is why we did section 8.3 first. You have to make sure that you master how to handle a lot of these trig integrals, because that's going to be our punchline to get to the solution on a trig substitution. So again, the whole point here is we're going to eliminate the radical. I want it to go away. We're going to use trig, so that means trig is going to be in our integral. And when I see different setups like this, I know exactly what I should be doing for my trig substitution. What I want you to recognize here is this is kind of what's in the form of the arcsine derivative. It's a number squared minus a variable squared. So we're going to let u equal a sine theta. If I see that present itself in one of my problems, then I can do that. Okay, so thinking about question number 6, that's a perfect setup. See how 9 is your number, that's your A. A is going to be 3, and u is going to be x. I have a number squared minus a variable squared. I am going to eliminate that radical by making this swap right here. I'm going to switch everything over to that trig function. Okay, now if I see it reversed, right, where it's the x, it's the variable function of x squared first minus a number squared, well then I'm going to use the replacement here that u equals a secant theta. And that's going to work out wonderfully with all of our identities to provide a really good replacement for that integral. And then lastly, of course, if you see something under a radical, again, there's radicals everywhere here. If you see something where it's a number squared plus that function of x squared, and again, order doesn't matter when you're talking about this one, right? You could have something like this. Then we're going to use the replacement that u equals a tangent theta. So these trig functions are selected on purpose because they're going to work awesome with some other trig identities. And so I'll try to show you that. You should definitely have your formula sheet handy with all the trig identities that we've used, the Pythagorean ones. We're going to use some new ones today. We're still going to use the power reducing. We'll also use the double angle formula today. So definitely have that handy because you get that. You get to use that anyway during the Unit 3 test. So it's nice to become familiar with where things are on that formula sheet. All right, so we are going to start the next video by actually attacking problem 5 and problem 6.